Now I want to talk about convolution. Now convolution is an important technique. Now it is used to compute the distribution of x plus y when x and y are independent random variables. So convolution helps us to compute a new distribution function of x plus y if you are given the distribution function of capital X and capital Y. So the density functions are given to us as small fx and small fy. So the first step is we want to get this capital F of x plus y, that is the distribution function of x plus y, and this distribution function f subscript capital X plus capital Y, this is what is called the convolution of capital F of x and capital F of y. So that is the distribution function of x plus y is called convolution of distribution function of x and distribution function of y. Now from the definition of the cumulative distribution function, so we have f of x plus y of some real number c is probability that x plus y is less than equal to c. So this is nothing but from the definition of the joint distribution function, or you can say a definition of a cumulative distribution function. So we have x plus y is less than equal to c. So we have two variables here, x and y. So basically this will be, you have to compute the integral of, so x and y are independent. So notice that we are not writing f of x comma y. We are writing f of x times f of y because x and y are independent random variables. And we have x plus y is less than equal to c because that is a definition of the cumulative distribution function. So again notice that for a cumulative distribution function, this is the definition. So instead of capital X, I'm just writing x plus y. So this was the definition. So till this point everything is clear. Now dy, we do not place any restrictions on y. So y goes from minus infinity to infinity. So this is dy here. This is the first integral here. But we worry about dx. So notice that we have y is going from minus infinity to infinity. But we have this restriction on x plus y. This is less than equal to c. But it could go from minus infinity to c. So that is our restriction right here. So we rewrite this. You have c minus y, and then you have minus infinity minus y, which will again be minus infinity because y is pretty small compared to infinite. So that is why we have this x ranges from minus infinity to c minus y. You have this dx, this ranges from minus infinity to c minus y. So I've just taken this dx right here. So we can do that because these are independent variables. So we can first integrate this. Now if you integrate this, you get f of x c minus y, because again so this is same as integral from minus infinity to c f of x x dx. So instead of c, I have c minus y, and therefore you have f of x c minus y. So instead of c, you plug in c minus y. So now we get this thing. So now you differentiate both sides. So again, if you differentiated this expression, then you obviously get f of x c. So yeah, we are going to take derivative of this side. So this will give you f of x c. So because derivative cancels with the integral, and this c comes in place of x. So that is what we get. So you differentiate this side. So d by dc of f of x plus y c, that is nothing but this expression, and d by dc you take inside. So d by dc of now this f of x c minus y is f of capital X c minus y, and f of y dy, this remains as such. So this is precisely what we get is the joint density function. So we have been able to get the joint density function of x plus y. So if you know the independent density function of capital X and capital Y, you can get the joint density function. And this will make much more sense once we do a couple of examples.